Good morning, good afternoon, everyone. Pleasure to be here today. I'll walk you through the content of today's webinar and hope you will gain some insights into some of the security challenges for vehicle computer and how that enables SDV. Strategy for today's webinar, we'll tackle this in a high level. We talk about the SDV concept, and then we drill down into different layers of the SDV, the E architecture as a key enabler of SDV, and then we drill down into the vehicle computer itself, and then the core of the vehicle computer, and discuss some of the security use cases. Before I deep dive, I would like to introduce myself. It's Omar Al-Shabibi. I'm lead product manager at ETAS Canada, and I love fixing market challenges by creating solutions that fulfill these challenges and create a mutual benefit for the business and my customers. So this is the agenda as we talked about. This is, think about it as a macro level discussion. What is the SDV concept in high level? And, and we take into the vehicle computer, why you need the system on chip and security challenges, and then at the end we'll talk about ETAS solution and then leave some time for Q&A. So one of the main goals of this webinar is to share a background and understand security challenges for vehicle computer system on chip. This is important. It's not just about talk about solution, but what are the challenges and how could you address these challenges? In addition, we will generate insights and hopefully, you guys as well, into security implementation of the vehicle computer around some use cases. And then finally, you will hear about our solution and how that solution is tied back into these challenges and tied back into the SDV strategy overall. Let's talk about, 200,000 feet view about SDV, software-defined vehicle. What are the benefits and the value out of these benefits? But before we deep dive, what is the SDV concept in a very, very high level? I would say SDV, it's a computer on wheel. And what does that mean? It means nowadays, vehicle, if it's SDV enabled, you have a different advanced software functionality in your car that enables drivers to interface with their vehicle as if it's their phones, right? It adds a new experience to the driver, increases automation, and that experience on its own, it's a transformational from classical traditional vehicle into advanced software functionality in the new vehicles. It's think about it as the vehicle in the classical way leaves the dealership lot, and after a year, it's the same vehicle. With the SDV enabled functionality, the vehicle leaves the dealership lot and it's a different vehicle a year from now. Why? Because it has the ability to add additional features, additional functionality that enhances performance, experience, and that what is the value of the entire ecosystem. So meaning it's SDV created a new ecosystem between the automotive OEMs, the automotive suppliers, and the consumers or the drivers of that vehicle. It's a new era of mobility and automotive industry. So we talked about the driver experience, right? So this is an important thing. Your interface with the vehicle, you have ability to download application into your car, interface with your car as if it's your phone, like with the advanced infotainment system, and that on its own it adds value and adds benefits to the drivers. The vehicle with that functionality, it does establish a new business model for the OEMs. OEMs have the ability with that advanced functionality to generate additional revenue opportunities in the future. Because a vehicle is always connected. You can download applications to it. Improve performance, add functionality, and that on its own creates like a loop between the vehicle and the OEM and so forth. It does establish feedback loop, as we said. That feedback loop is very important. The vehicle has the ability to process a large set of data and gather that data, create perception, and then also transfer that information back to the OEM. What does that do? It helps the automotive engineers at the OEM to improve the design, the development cycle, and identify gaps for future releases, and that's on its own, it does add tremendous benefit to the OEMs. And in addition, it does enable preventative maintenance, and it saves costs for any problem in the future. If you have some issues, whether it's a software issue, whether it's some updates you want to have, update bug fixes, vulnerability, you have the ability to push updates into your car without actually sending the car into the dealership and spend a lot of money on it. So that means there's that ecosystem generates that the value to the OEM, and of course in return the driver experience now is different. We talk about all the ADAS functionality and autonomous driving functionality. With all this ability to gather such large amount of data and process this data and add additional perception to the driver and additional safety, right, combined with the advanced ECUs, that it's on its own. It becomes now an expectation. You have all the different sensors in the car that prevents accidents and so forth. With that overall, functionality, you have enhanced cybersecurity solution for your car, end-to-end cybersecurity. To me, is to enable that SDV and to have that feedback loop, have the software update, firmware update on your car. You need to consider security in place, and we'll talk about it more in depth in this webinar today. So, in a high level, this is a new ecosystem, and I will call this is a new era of the automotive industry, as explained previously. If we deep dive now into how do you realize that advanced software functionality in your car, how could you transform that driving experience from the classical traditional vehicle into an advanced software-defined functionality and create that perception to the driver and have that connection between the drivers and the vehicle? Of course, you need to start with your EE architecture. EE architecture is electrical and electrical architecture of the vehicle. Nowadays, most of the architectures in distributed format, and there's always a transition. There's a transformation to go towards more domain centralized architecture, and all the way into having the ability to connect your car into a private or public cloud through the vehicle computer and advanced hardware and software functionality in your car. So that transformation is enabling and realizing software-defined vehicle. You need to have the foundation. This is like an important aspect of your car to have the ability to realize the advanced functionality in your car, to have more powerful computing platforms and more centralized EE architecture approach with the connectivity and continuous update in place. With that evolution and transformation from current EE architecture setup all the way to centralized vehicle EE architecture, you have increased security threat because you have large set of data you have to deal with, different software applications you're running. Now, we're not talking about just a classic middleware stack like the classic AUTOSAR. We talk about adaptive AUTOSAR. We talk about different POSIX operating systems, and this is like as a technology stack, but also you have to add to it the applications that you add into your car, whether it's infotainment-based applications or ADAS-based applications or different powertrain applications, that kind of thing that you need to have in your car. That increases the threats, and we talk about it more in depth as we move forward in this webinar. Now let's move into the vehicle computer and talk about vehicle computer in high level at a glance. What is vehicle computer? It's literally a computer system that collects, processes complex and high bandwidth data from different ECUs and sensors in the car. We talk about the advanced assisted driving system, infotainment, navigation, right? Powertrain applications. Within the infotainment system, you have the ability to like having streaming applications, and that this is very important. This is the new experience we talk about, right? And that cannot be realized with focusing on the classical microcontroller application or microcontroller domain. It does do a certain job, but you need to go into another layer, another level, where you have the ability to compute large set of data with having a strong core of your vehicle computer, and that core is called a system on chip, because most of these vehicle computers need the system on chip, to compute the large set of data and provide results and perception. So now we're adding into the vehicle more intelligence, more capable platform, and more processing power to optimize that functionality and provide the value to the entire EE architecture. So in a summary, vehicle computer, I would say it's a cornerstone, it's a foundation of the new architecture, and it's really hard without this to realize SDV. So you need this one. And of course, this depends from an OEM to another OEM, from an architecture to another architecture, how you can realize this vehicle computer. So we talked about the core of the vehicle computer, and that's SoC, but that is an evolution that it's happening in the automotive industry to go from a classical microcontroller into more advanced system on chip. You have more resources. You have the ability to run multiple applications. It's no longer a real-time CPU. You have multiple CPUs run on the same chip, and we talk about it again in more depth today. So you'll have less hardware, more software in the car, and that software is capable of updating applications. The core of the E architecture, the vehicle computer, is more capable of updating application, updating firmware, and throughout the entire life cycle of the vehicle. To move forward, we always have to, because this is where we're drilling down. So we started with SDV in a nutshell, and then we went into the architecture that realizes the SDV, and then we drill down into the vehicle computer as a core and cornerstone of the E architecture, and we talked about the system on chip that you need in the vehicle computer to realize all the advanced functionality and additional software layers that we talked about. Now let's connect the vehicle computer into security. So security, it's a critical aspect of getting SDV on our streets, meaning cybersecurity, I would say it's a prerequisite. It is a prerequisite. It's another foundation and a key pillar to enable software-defined vehicle. Think of it as constructing a high-rise building. You start with the foundation. So if you get the foundation wrong, it will be very expensive for you to update or maintain that building, and you have to always to come back and look into it. So security is a similar aspect. You start with it right from the beginning, consider it in your design, consider it in your process, consider it in your use cases, in the software implementation, and then throughout the entire journey. It's not a one-time event, it's a journey, it's a life cycle from the inception all the way until decommission. So that is because of why? Because you have constant connectivity with SDV. SDV is just, you can transfer data, you download data, and that what we said, the vehicle is no longer the same vehicle that leaves the dealership now. A year from now, you added more stuff to it, and you enhance the driver's experience and safety applications and stuff like that, right? It's happening through constant connectivity and continuous update. Now you have authorization and access management as one of the considerations that you need to have in place. Meaning, we talked about the different software layers, different technology stack, and different software applications that you run. I don't know, let's take a streaming, for example, right? So who can access what, how you run this application, and that control needs to be in place. Otherwise, if you open up this, you're going to introduce your vehicle into a vulnerability. Third-party software ecosystem and speed of software delivery. This is no longer a car that has a less interaction with the OEM. It depends if you buy your car. If you decided not to go back into the dealership and OEM, just fix it somewhere else, the connection is gone. That's it, right? In this situation with SDV, the connection between the OEM, the feedback loop, as we talked about, it's always happening throughout the life cycle of the car. So, and you have different software layers on the ecosystem that needs to be maintained, needs to be updated, and so forth. And you need to have your DevSec operation environment set up in place to have the ability to develop features, to test, merge, get your build, test your build, and then deploy your build. That mindset needs to happen in place on, and keep it into your consideration to move forward with this. So security is paramount when it comes to SDV, and it's a prerequisite. Now we talked about all these different layers. So why system on chip? Why it is needed? Because we mentioned some of these functionality. We talk about ADAS, infotainment, electrification are all driving the emergence of powerful on-vehicle computing platform. Because you deal with a lot of set of data. We keep talking the same thing. It's the same message on and on, right? You have to deal with, right? And that evolution transformation that's happening on e-architecture from traditional distributed EC to more centralized domain architecture requires that ability. So instead of having 10 ECUs to do certain things, now you can combine with the domain controller. And we talked about the value add and customer experience. And finally, that software-defined vehicle platform can be realized with the high computing SoC. Because it has proven that it's more capable. Of course, it has more resources, and that microprocessor is very powerful to enable the advanced functionality in your car. The SoC itself, has the ability to combine security, safety, and performance, and it achieves the holistic goal of these three parameters. So here is, you don't need to focus on performance only and get a lot of applications run. You need to consider safety. So meaning you have within the same SoC different computing islands, which we'll talk about them shortly, and each computing island responsible for a certain job. Excuse me, responsible for a certain job. And that, you can isolate this. You can say this is a safety island. This is, regular normal world island to do certain job. And how you can orchestrate security with these different computing islands within the same SoC. So now we had the ability to combine safety, security, and high performance of these ECUs eventually. And SoC has the capability to do this. Now, we talked about all the nice story from SDV, e-architecture, vehicle computer, SoC as a core element, and the value that adds to the advanced functionality. You actually cannot realize advanced functionality without having that element of computing, advanced computing SoC and powerful vehicle computer. Now let's talk about the challenges. All these benefits that we talked about, they come with challenges as well. So we talk about challenges from a security perspective and how this is related into the current SoC and how can we address these challenges in our proposed solution. So you can see here, this is another 200,000 feet view of the SoC. You can see in this diagram, you have multiple computing islands on the same die, on the same chip that does a video and image processing, like has AI capability, graphical capability, sensor management and sensor pairing, safety CPU and security CPU, and so forth, and different hardware peripherals within this SoC. So these computing islands within the same chip, with heterogeneous and diverse architecture from one SoC to the other SoC based on the application and the use cases. And they have also shared resources such as external flash. So we can see most of these SoCs nowadays, they don't have internal flash because of size and optimization. So it's always external. So you have to deal with that external resource now. That architecture introduced another challenge in terms of managing and implementing cybersecurity. So the task of managing security content has become more complex with this type of architecture. The security use cases remain the same. to be honest. You still need to have a secure boot because you need to authenticate and trust whatever application that you're booting in your ECU. You need to have secure communication from one ECU to the other and the surrounding components within the car, right? Protected and secure communication. You need to have secure diagnostics if you want to access the ECU to download some stuff or pull some log files, how you have access, what service that you use, secure update, and stuff like that. So security use cases remain the same, but the implementation and the development of these use cases actually have changed because now you have a different ways of looking into this, and you need to have a different mindset to approach the problem and come up with a solution that it's ensuring trust, authenticity, and integrity in place without compromising performance and without compromising safety. So with this challenge, with this overall SOC security challenge that comes out of the current architecture and design, we'll touch base on this when we talk about how ETAS is addressing this challenge and the proposed solution that's actually being tested and prove that it's capable of alleviating these concerns to our customers. Now, before we go into that solution, I would like to talk about important use cases, security use cases when it comes into vehicle computer. And to be quite honest, they also apply to other ECUs, but we're talking about it from advanced functionality ECU like vehicle computer. So why we picked these use cases? Because we wanted to have that ecosystem in place. Just not talk about SDV and the architecture and the SOC and security challenge in general, because that's pretty much it is a truthful problem, and it's a problem that exists. But we wanted to be more concrete in the way that we want to tackle these problems in some of use cases. So we picked these two use cases: secure manufacturing or provisioning use case. The other one is lifecycle, and then we talk about it today. So before we deep dive into the provisioning use case, what is the challenge that provisioning use case has? And then we offer a solution to this challenge. So how to establish root of trust starting with the manufacturing provisioning of the ECU is one of the key challenges that provisioning use case actually experiences. So at the beginning, you have an ECU that, nice, well designed, well architected, sitting on production line, and you want to get this actually deployed in the car, but you need to load software on it, you need to load your firmware on it, you need to test, make sure it's working, and then it does go to the assembly and you assemble the car with that ECU, right? But before you deep dive into this one, you need to have established root of trust. Like, how do you trust the application that you're downloading into the ECU, right? How do you ensure that there is integrity in the data that you download? How there's authenticity in the data that you download? And that's what we call root of trust. Root of trust starts with injecting cryptographic material in your ECU. It's like cryptographic keys, let's say, to be more specific. And these keys, they accompany the messages, the content, so you could use to cryptographically confirm that the content that you're downloading into the ECU is authentic, it's trustworthy, and it's an ECU ready to go into an assembly line. So that is the root of trust establishment, is basically to inject a cryptographic material into your ECU and then start the download software and firmware applications into your ECU. So let's take an overview of secure provisioning use case here. Key provisioning is a system-wide thing. It does include the backend of the OEM, the key management system, the production line, of course, the test bench, the engineers or test verification engineers that you have in your environment, and so forth. So this is, you need to look into this from a system perspective: OEM, tier 1 supplier, security supplier, and the other stakeholders involved in this operation. Manufacturing key provisioning is a critical use case that allows the OEM to inject their own cryptographic key material into the security module of the SoC. If you remember on the previous slide, we talked about the different computing islands within the same SoC, and each SoC has a dedicated security core to govern and perform the security operations and protect the crown jewels, I call them, which means the cryptographic material from accessing being exposed, I would say, to the other CPUs within the host. So that's the hardware security module. This is like the general industry name. Of course, from one SoC to the other SoC, they have different names, but this is what it's known in the industry nowadays. The key container, when you have the keys, is a provision to the vehicle computer, needs to be cryptographically secured, means you have to encrypt them and make sure this is secured, whether you have manufacturing planned by the tier 1 supplier or by the OEM or by some other third-party contract manufacturer here. So you need to have this in place to ensure authenticity, trust, integrity, and have flexibility in your design. The hardware security module of the SoC needs to decrypt that key container because you encrypted it. You need to download it now, inject it, decrypt it, and during the provisioning step, and then re-encrypt that key container with a device key, and then saves it into the key store and external flash. That's now you ensure the end-to-end use case securely implemented. Now we talked about the challenge and how to establish root of trust. And this is an overview of the use case. Let's move into what is the proposed solution. So at the beginning, you have hardware security module that you would like to inject or provision the encrypted key container, whether you want to have a key container downloaded or one key at a time. It depends on your design, implementation. That's a different way of doing things. It's possible. So one of the proposed solutions, for example, it's not the only one, you could inject a pre-shared key that is defined by the OEM and in collaboration with a security supplier and the tier 1. That pre-shared key can be injected along with the HSM security module, security firmware binary, and then provisioned into the SoC. Security module of the SoC. Now, when you do provisioning of the cryptographic material, you download them, use that pre-shared key to decrypt the encrypted key container, and saves it into your key store. Now, in this case, you've guaranteed that the entire system end-to-end is secured, protected, confidential. And that keys are not leaving the environment unencrypted, and you have your system secured with this process. This is an example of a high-level provisioning deployment. It's different from one OEM to the other because it's connected overall backend system. So let's start with the OEM specific. So you have your manufacturing provisioning platform, the KMS platform, or depends on how you manage that, and has access and interfaces into the ECU and specifically to the system on chip of the ECU, and more in particular can inject things into the secure CPU inside that SoC die. So it could happen either through the microprocessor application CPU, depends on your design and your manufacturing environment, or the real-time CPU, which eventually download the keys that inject the security objects into the security module, security CPU. Once we talked about the decryption happens, re-encryption happens using the device key. Now the application can ask the security module to save the encrypted keys into external flash that it's outside the SoC to ensure persistency. So moving from left to right, you can see here in a 200,000 feet view, you've achieved security, confidentiality from the way that you injected your crown jewels, the cryptographic material, all the way until it gets saved into the external flash. So what is the summary of this use case? Manufacturing provisioning needs to be secured end-to-end. This is our recommendation. This is a best practice of security, and enabling that there is a trust in the system and also some sort of business model flexibility. Manufacturing provisioning use case ties back into the OEM, automotive OEM key management system, and it's different from one OEM to the other. And like in terms of the encryption algorithm that it's used, in terms of the implementation, in terms of the software application that it's ties back between the key management system and eventually deployed on, excuse me, on the SOC and so forth. And then that is the entire system-wide application and implementation that includes several stakeholders to implement secure provisioning. So let's deep dive into another use case, which is the life cycle. And what is life cycle? What is the benefit of the life cycle? And what is the challenge of the life cycle? And how are we proposing a solution for this challenge? So how could the OEM ensure ECU lifecycle is secured? This is important, and we'll talk about this more shortly. This is another overview of lifecycle. So to get everybody on the same page, to understand what the lifecycle means and how we're going to talk about it. Lifecycle simply dictates who can have access to what, and this is important to have such access restriction in your application. Secure lifecycle enables unrestricted access, as we said, from different phases. If you have just manufactured your ECU or you're using it on development and test bench by the engineers and testing team, or it's actually ready to be assembled in a car and goes all the way into field, in operation, and then until the end, which is actually decommissioned. Lifecycle is a security designation state of the ECU. Transitioning of secure lifecycle from one state to another requires the following aspects. Anti-rollback measures is essential. You don't want to deploy a firmware or software, and then all of a sudden you use the old one, right? And then that has either vulnerability or bugs or performance issues, whatever, right? So you need to ensure that in place. So SOC security needs to detect and react on rollback attempt. Elevated privileges required for transitions. This is important to go from one aspect from one phase to the other phase. And anti-rollback ensures forward direction of lifecycle state. You always go back. You always go straight, not backwards. So, what is the proposed solution to the challenge of how we actually make sure this is secured and in place? We're suggesting to have like a 5 high-level phases. Of course, this could be different from application to another application. So manufacturing, and you're in the production plant, you're producing ECUs. Either you send them to development team and testing teams, or you send them into an assembly line, right? And then from assembly line goes either to return for debug and analysis, or goes back into decommission if that's end of the story. From development all the way goes into decommission. The key message out of this slide is transition from one state to another is based on the arrows here. So there is no way back. You cannot go from development to operation. You cannot go from operation to manufacturing. You cannot have a return or decommission ECU to make its way back again to operation. That it's not should not be the case. And this is why you need to have lifecycle. You need to have lifecycle. You need to secure it so you don't have to change it, and it's not easily to change unless you have certain privileges and certain access management rights to make sure that this state can change. Manufacturing ECUs in production plant, host debug is enabled. Some of the security measures can be less restrictive because it's not yet in fully operation environment. Operation means it's in field, assembled in a car, and cars on our streets. Security measures are all activated, and you cannot access without having privileged access rights based on your diagnostic messages, based on debugging messages that it's actually secured and enabled by the OEM to their licensed dealerships. Development environment, this is ECUs and engineering development state. We all, as an engineers, we need ECUs to work on, to test, deploy software, identify gaps, problems, testing, hardening, verification and validation before it goes into operation. Security measures could be less restricted, such as debugging. Return, the state is you send back there's a faulty ECU, needs to be debugged and analyzed. The state requires access to secure logs. So you still need to have security measures in place to protect the confidentiality and intellectual property of the OEM. This is very important. In return and decommission states, it's important to protect the intellectual property of the automotive OEM. Finally, decommission, it's a final state of lifecycle. Confidential material end user must be erased and no possible access to the ECU. So you don't have to, you don't need to get access to the keys and have the ability to extract content, some data, personal information, and stuff like that. This is very important. So that's why you see that lifecycle state, it's a real security designation, and it's very important, and you cannot move from one to the other without having certain access rights in place. In terms of lifecycle, you could achieve secure lifecycle in two ways, or two formats: it's hardware and software. Secure lifecycle state can either be software or hardware, as we said. Hardware is based on one-time programmable memory or registers, and the HSM could have or might not have the ability to access the OTP, to read, either access or have an API, for example, to read the OTP status and see if it's the bit flag, 1 or 0, depends on your design, and whether it's actually enabled or not enabled, means it's a hardware lifecycle secure state, and hardware-based lifecycle always superior to software because it's programmed via eFuses, and that's where you get the benefit out of this. Hardware lifecycle always takes precedence over the lifecycle in a combined environment, and combination of hardware and secure lifecycle depends on the OTP design of SoC. So software-based lifecycle, it needs to be securely stored in the external flash. You could have it as a separate entity or part of your key store, depends on how you want to design it and do it in that way. So this is important aspect, and SoC on its own, we talked about it. It doesn't have a flash inside, it has external flash, so it means you have to save that state and put it back into your external flash and read and decide on the state of the ECU. What is the summary of lifecycle state? Secure lifecycle is a critical aspect of the vehicle computer ECU or any other ECU within the vehicle architecture. Protecting lifecycle is a must-have to prevent any manipulation of the ECU content. We talked about the security privileges and access management, and this is an important parameter to be considered. Hardware-based lifecycle always takes precedence over software-based implementation. Anti-rollback protection is an important measure of implementing secure lifecycle. So with that, I conclude the two use cases we talked about, the security provisioning use case and the lifecycle state. And I want to just go back and to remind you of the SoC architecture and the diverse architecture of that system on chip as a core component as part of the vehicle computer. And what is the proposed solution this from ETAS perspective? So what we have done at ETAS, we've identified the problem by listening to our customers, working with them, and adapting to what is the possible solution could look like to alleviate these concerns and maintain security, safety, and also performance all combined. So ETAS, we've developed Cycler SoC, which stands for Cybersecurity for System on Chip, and it's embedded cybersecurity software solution for the security module, the HSM, and the other CPUs and the same SoC. What does that mean? So you could look into this 200,000 feet view diagram of automotive SoC, and the bottom you have the different CPUs module, security module, real-time modules, microprocessor application CPU, and the upper layer is the software. So the software that we have comprises of the HSM firmware plus the host components that are actually integrated into the other application layers, into classic, adaptive, and POSIX environment to enable the interface with the security module, but also have the capability to do some crypto operations outside the HSM, because now we have more resources to do this, and we have that capability by ensuring and maintaining the keys in the HSM and in a secure environment, and without exposing the crown jewels outside the security module. So this is the way that we've designed the solution, and we implemented it. And we have the HSM-based implementation and also the TE-based implementation, where there is a solution that actually fulfilled that TE use cases by having Cycler SOC component runs on TE environment. So this is our solution to the foreseen problems in the market. What does it do? It provides security functionality for the SOC platform, enables secure diagnostics, secure update by establishing root of trust, as we talked about it, enables system authenticity and integrity, and offers cryptographic protocols and algorithms to the application and fulfilling the automotive use cases. So Cycler SOC makes the integration of security implementation, security components easier, leveraged the different computing islands of the SOC, and fulfilling the automotive use cases that it's more important to our customers. So this is the overall, and of course used in advanced functionality in ADAS computers, and have the ability to support multi-tenancy, POSIX, and application such as adaptive and classic AUTOSAR. So this is the a high-level definition of the features and functionality. It has the ability to do secure storage of data and keys in the external flash, trusted channel amongst different cores of the CPU, multi-CPU tenancy, including virtual environment. Right, this is important nowadays. The SOC has the ability to run POSIX, has the ability to run hypervisor, to create, and achieve isolation and separation of different applications. So we have a component as well that could run in hypervisor. So this is, the modular architecture that we've designed in our product to address the diverse architecture of these SOCs. And of course, store and manage keys in the external flash. The HSM has no longer sovereignty and control over the flash because it's external to the SOC, but that design, that implementation we put in place, you still have access to the external flash, and also the content that it's actually loaded is encrypted and secured. Secure application, a secure startup, authenticity, access management, and lifecycle, as we talked about it earlier. So to move on, and what is the value that we are introducing into the market? It's a modular solution that is fulfilling automotive use cases and making integration easy to our customer to save them time and cost. This is very important. And what we are trying to focus on our design, because of the complexity of the SOC, we're also introducing a zero trust concept in our design and our implementation. We as a security experts, we have that mindset to put in place. We're taking the zero trust concept as a specific and literal meaning. Don't trust all the other applications, don't trust all other CPUs, and focus within the security module, but orchestrates all the security implementation and use cases, and introducing that solution to achieve that zero trust concept. And it's really important that, to have this in mind when you design your security software. So the thing that makes us different than others, have the ability to customize some of these use cases based on the implementation, have the modularity in our solution, and as you saw, different components that can be integrated with different applications, make use of the security module, or also have the ability to perform some host-based hardware acceleration. Also depends from one SOC to the other. You might end up with some SOCs have multiple hardware accelerators, so you can leverage that advanced functionality and use them and benefit from them. And we talked about compatibility, compatible and seamless integration of AUTOSAR stack, any AUTOSAR stack, and POSIX operating system with zero trust concept in mind. With that, I conclude today's webinar. I hope you guys have gained some knowledge today, and please stay tuned for our podcast on SOC security. Subscribe to our podcast at Buzzsprout and never miss an episode again. Thank you so much. Feel free to reach out to me, omar.alshabib@etas.com, to listen to your challenges and work with you and others to provide solutions. Thank you.